Let's talk about some common power series. It says down here, if you memorize these 3 power series and then you stop and you say, well, 1, 2, 3, 4. Oh man, there's 4 of them. The first 3 are the most important. You'll need to know all 4, but the first 3 are the most important. Okay, take a look at what you've seen before. The general form of a Taylor series is this structure right here. You've seen it, you've dealt with it, and I'm going to focus on this term, which is the explicit term, which is the term that takes you directly to whatever term you want. Take the nth derivative, evaluate it at c, x minus c to the n over n factorial, right? Well, if this, and this one is, if this was an infinite series, infinite number of terms, you could write it like a series, and you would say, okay, fine, let's plug in a 0 in here and add up what you get when you plug in a 0, what you get when you plug in a 1, what you get when you plug in a 2, and a 3, and a 4, and a 5, and do this all the way to infinity. And when you do, you will, this is huge, you will be able to take this function, e to the x, and approximate it as a polynomial. You can write e to the x as a polynomial, like x to this, plus x to that, plus x to this, with some numbers and coefficients, and it's great. So much fun. Watch this. We're going to write the Maclaurin series for the given function. Okay. Maclaurin series is centered at 0, and I don't have space, so we're going to just jump right in. Here's what we like to do in this, we being people that teach this stuff. We like to do what I call, this is an awkward title, I call it pattern sniffing. I'm going to find some patterns. I want to figure out what the nth term would be. So in just a few minutes, we're going to have a power series for e to the x. If you want to get ahead, you could say, well, I'm going to grab my purple pen and I'm going to write some stuff down, and it's going to start at n equals 0 and it's going to go to infinity, and there's going to be something here. And I don't know what that something is, but that something is going to, if I take this all the way to infinity, should give me e to the x. Okay, so let's keep moving. What I would like to do is find a few derivatives, and this is going to be super boring at first. So f prime of x is e to the x. F double prime of x is e to the x. F triple prime of x is e to the x, and no one is confused at this point, right? So what I do is just do a few of them till I find a pattern. Didn't have to go far on this one, could have stopped much earlier. But you continue until you say, okay, well, the nth derivative evaluated it, well, the nth derivative is e to the x. Now I'm going to evaluate them. Now, often there is a much less obvious pattern here. It might be e to the x, and this would be 2e to the x, and then this would be 4e to the x, and this would be 8e to the x. And you would say, okay, now how do I deal with the numbers in these patterns? You would have to do that a lot. Not in this one. This is a good starting point. What we're also going to do is figure out what happens if I plug in 0, and I'd have e to the 0, which is 1, and f prime of 0 is 1, and f double prime of 0 is 1, and f triple prime of 0 is, this is getting boring, and so it doesn't matter what derivative I'm evaluating. At 0, I get 1. Okay? All right, so check this out. This is what's really going on. I'm going to grab this other paper. I'm trying to plug things in to this general formula right here. Keep circling it, and there we go. So this series is going to be f of x, f of x equals e to the x. I was about to write it differently. And it would be f of c x to the 0 over 0 factorial. If you're not writing this part, that's totally fine. Plus, f of 0. And then f prime of 0, x to the 1 over 1 factorial plus f double prime. So what I'm really doing is just filling in some gaps till I can find some patterns. This one's a lot more obvious. And then I'm going to get to f nth derivative evaluated at 0, x to the n over n factorial. And this one keeps going because it's going to be an infinite power series. All right, so if we did this, we would say f of 0, well, that's just 1 times 1 over 1 plus, okay? 1 times x over 1 plus 1 times x squared over 2 factorial. Let's do this term that would be 3. That would be 1 x cubed over 3 factorial plus 1x to the 4th over 4 factorial plus dot, 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 and we would eventually get to the nth derivative evaluated at 0. Well, we've sniffed out the patterns enough to know that's 1 x to the n over n factorial, and then it just keeps on going from there because it's going to go on forever. So here's the wonderful thing about e to the x. E to the x is this. If I graph e to the x, and then I graph 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24, and then maybe a few more terms, I'll have a really good approximation, and I want to show it to you. Check this out. Might take a second for me to type, so feel free to skip a bit. I will type very fast. 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. We'll stop there. They should be pretty close. Should be. There's e to the x. And all right, now I say they should be pretty close. And they're not, okay? They're not here, but that's the point. We only did up to this, but look here where it's centered. If I zoom in at around y equals 1, you're going to see how amazingly close these are, and that's the point, because a Taylor polynomial is an approximation at a specific point, and in this case, the more terms I have, the more accurate it will be the more accurate it'll be further out, but then at that point, it is so super duper accurate, they look like they're basically the same function. Super close. You could go to the table, plug in a 0, and you get the same thing, or you better get the same thing there, but if I plugged in 0.01, I get practically the same thing. They're off by just a smidge. Look at that number right there. They're exactly the same until the very end, right? That is super close. And that's the point of an approximation. And you'll hear this said in other parts of the videos, and I just want to point it out because it's fresh on my mind. I was talking to a friend of mine who is an engineer, and he uses this kind of stuff to make approximations. And I thought, well, why would you use an approximation when you can get the exact thing? Because of the computational power required to do the exact thing all the time. I know computer chips can be cheap, but still, if you are putting some computer chip in something and you want there to be some computations that are done, the simpler the chip, the cheaper it is, the better your product will sell. So approximations are sometimes just good enough, really, to do whatever needs to be done. That's why this stuff is so amazingly practical, one of many reasons. Okay, but if I want, and let's go back to a normal sized window that we're used to seeing, the standard window. If I want this to truly be the full thing and not have this little tail wagging up here and it's like, what in the world is that? And it doesn't even match, and you can see where it gets off a little bit up here too. If I want this to be completely accurate, what should I do? Well, you can't, but theoretically, I could take this out all the way to infinity, and I'm not going to, but I'm going to try. This is going to get a little tricky here, but check this out. I'm going to write this as a sum. This is the sum from 0 to infinity of, now what's the pattern? That is the pattern. That is the explicit form right there. So x to the n over n factorial. If I added up an infinite number of terms, I'd get this, and this, and this, and this, and this. And we saw that it was accurate to a point, and then another, and then another, and then another. And then all these discrepancies that become really obvious over here disappear. The further out you go, the more accurate it's going to be. So I want to prove that in a second on a calculator, but back to the first page. And you'll need to do this at the end of each of these. The rest of these are not going to be done on paper, so you'll need to remember to go back and do this. But at the end of each of these, we're going to write down what we just found. This was x to the n over n factorial. All right, let's go back to here and let me demonstrate to you how the more terms we have, the more accurate it'll be. So y equals, and I'm going to clear that out, and I'm going to press math, and something we've never used before, I don't think we've used it before, is summation. And we're going to start at n. from 0 to, and let's take this ridiculously high. Let's go, I'd say 100. I'm not sure if it has the computational power to do it. Let's just go 20. That's disappointing, right? X to the n over, oops. Lost my place. Over n factorial. Factorial is, in case you care, under the math menu, go to probability. There it is. There we go. It's going to take it a minute to figure this out, but we're going to graph and just sit there and watch it happen. There we go. See how accurate that is? Look how accurate it is right around there. And then it gets off here. So the more terms, the more accurate it will be.